Hi, and welcome to this short clip reviewing some of the effects of intermolecular forces on lattices and structures. So the clip will look at how different intermolecular forces will affect the structure of a substance on a larger scale. And as we go, some attention will be paid in passing to physical properties and its effects on them. So substances can be classified into ionic, polar covalent, or non-polar covalent. And in terms of intermolecular forces, with ionic substances there's no molecules anyway because it's all just an ionic lattice, so there's no intermolecular forces to speak of. On the other end of the scale, when you get non-polar covalent bonding, only London forces are present. There's no permanent dipole-dipole interactions or hydrogen bonding. And this leads to a gradual change in certain physical properties. For example, the boiling point decreases, the solubility in water decreases, or polar solvents for that matter, and you get a decrease in electrical conductivity. So, let's have a look at some examples. So if we start at one extreme by looking at ionic substances, as you know, there's no molecules present, just a lattice of alternating positive and negative ions. There's no intermolecular forces because there's no molecules, so all properties are based on the giant ionic structure. So NaCl is simply the formula unit. So if we now look at water, or more specifically ice, there's a number of features that ice has that makes it anomalous compared to other polar covalent lattices. So the first one is surface tension. The second one is lower density than expected when in the solid state. And this is due to the open lattice. The length of the hydrogen bonds keeps the H2O molecules a little bit further apart from each other than you might expect. So this means that ice floats on water. And finally, you get much higher boiling and melting points than you'd expect due to extra energy needed to overcome and break the hydrogen bonds. So I'll leave a slightly better diagram than one I could manage that shows the hydrogen bondings side on very clearly. So that's water in an open lattice as ice. So if we move on to non-polar covalent bonding, within this category you often get what we call simple covalent structures. So an example might be iodine. I know it says ClCl in the strip halfway up the screen, but the graphic I've found has iodine, and it illustrates it quite nicely because it shows that there's strong covalent bonds within each iodine molecule. These do not break during melting or boiling. I emphasise that because it's a very common mistake that people make when they're describing this in exams. So in this type of structure, it's the London forces which break during melting and boiling, not the covalent bonds between the iodine molecules. So the same would happen with chlorine, with fluorine, with oxygen, or any sort of simple covalent structure in the solid state. So finally, let's have a look at some of the effects of these different forces and bonds on the boiling points or the melting points of a range of elements, just to put it into context for you. So we've got a range of elements here. What I'll try and do is classify sections of this graph according to what intermolecular forces or bonding is present. So the elements highlighted in purple are simple non-polar covalent. And the ones that have larger atoms and molecules have larger melting points due to stronger London forces. So giant covalent structures have no intermolecular forces as multiple covalent bonds between the atoms in the structure. And this means many strong covalent bonds require lots of energy to overcome. And finally, giant metallic structures have strong electrostatic attractions between positive metal ions and delocalized electrons. And obviously I don't need to remind you there's no intermolecular forces in metals. because there's no molecules. Okay, so hopefully this little roundup put some of the stuff we've been talking about into perspective. Hopefully it's been of some use, and once again, thanks for your time and see you soon.